Hi everybody, this is lecture 12 and today we're going to do something exciting. I'm going to show you how to compute line integrals. So we're moving on to new kind of calculation that you're going to do. So the stuff I show you how to do today, I recommend that you practice on your own, especially right now that you're just learning it, so you can follow along the course with greater ease as we move forward. Okay, so let's do that. So we're going to be doing integrals over curves in the xy plane rather than regions of the xy plane, which are two-dimensional shapes in the plane. We can also integrate over curves in the plane or in three-dimensional space. So before I tell you about the integrals, I'm going to tell you about how we're going to describe the curves when we do the calculation, when we do the integration. So we're going to describe curves using a parameterization. So so let me just show you what a parameterization is in an example. Right, so our example is going to be a familiar one. So we're looking at the curve, at the circle of radius 1 about the origin. So this circle radius 1 about the origin. So this circle has two descriptions. Like any curve has two descriptions. Sometimes it's easier to work with one. Sometimes we want to use one of these descriptions to work with the circle. Sometimes we want to use the other. So here they are. So there is the familiar implicit description. And that's, so to describe the circle implicitly, I'll just give you its equation. I'll just say the circle is a set of points, x comma y, which satisfy the equation x squared plus y squared equals 1. Right, so this is implicit because it doesn't give you any points. If you want to, so it gives you an equation. If I give you a point, maybe 1, 2, does it satisfy this equation? Well, 1 squared plus 2 squared is 5. Which is not equal to 1, so no, 1, 2 is not a point of the circle. Right? You have to work to get points in the circle. So that's why it's an implicit description of the circle. The alternative to an implicit description like this is an explicit one, but we refer to it as a parameterization of the circle, or of the curve we're looking at. So in this example, so the alternative is a parameterization. Let me just, Okay, so the parameterization is pretty simple. I'll just say that on the circle x is so we're looking on, so the circle consists of points with coordinates x and y given by cosine of t and sine of t for some number t between 0 and 2 pi. Okay, so the parameterization is the explicit description of the circle. I'm saying I'm looking at points where x is cosine of a number and y is sine of that same number, and the number is between 0 and 2 pi. But here so t here is the parameter. Right, that's where the parameterization takes its name from, and the upper bound 2 pi. So it's in here to ensure that the circle is that as t goes from 0 to this upper bound, the point cosine of t comes sine of t. So it's going to move around as t increases, and it's going to cover the circle exactly once. So so the parameterization covers the circle. So the whole circle, every single point in the circle is of this form for some t, but there is no repetition, so exactly once. Right, so I say once because if t went from 0 to 4 pi, then I would cover the circle twice, but here we just want to cover it once. So this bound is important So the bounds for t are important because they tell you what shape we're looking at. For example, if we were interested in the half circle, in the upper half circle, then I would say that t goes from 0 to pi, and then I would just get the upper half of the circle. But if I want the whole thing, I'll take t between 0 and 2 pi, or for example, between minus pi and pi. That would work too. What's important is that I cover my curve exactly once. Okay, so this is the general picture this is a parameterization in the case of the circle. Let me give you the general idea. Oh, before I do, I want to repackage these two formulas here in a single entity. So same information, so same info. I can package these two functions, cosine of t and sine of t, by putting them in a vector valued function. So I'll give you a vector valued function r of t, and say that with components cosine comes sine of t, and I will tell you the t ranges between 0 and 2 pi. So that's another way to describe the parameterization. Okay, now let's look at the parameterizations in general. Right, and I recall the reason I'm doing this is because when we do integrals, when we do line integrals, we don't want an implicit description of the curve of the domain of integration. We want an explicit, a parametric description. So we're going to have to parameterize curves. So in general, we're going to have a function r of t, and then it's going to, a vector valued function r of t, and it's going to have two components. In 2D, and in 3D, it's going to have three components. So you can just imagine a z of t in there. And also I'm going to have a range for t. I'm going to say that t ranges between two numbers a and b. And these inequalities can be, strict or not. I mean, it's up to you. You can imagine the variations. I could have this, for example. Okay, so this is a parameterization. And here's what it looks like. So it's going to be, some curve in the. So this parameterization is describing a curve in the xy plane, and it's maybe this curve over here, right? The parameter t lives on the t line. I'm going to draw the t line down here, right? And the parameter t ranges from some number a, maybe here, to another number b, and t could be anything between a and b, and then this point, so the start of the curve, so r of t, so r of a is going to be one of the two endpoints. So so in general. Okay, so r of t is going to be one of the two endpoints, so perhaps this one. And r of b is going to be the other endpoint. And r of t is going to be something in between here. Right, and you see that as, so this function, just sends a number a to r of a, just sends t to this point in between, and b to this point at the other end. And so you see that as t increases from a to b, the point r, I traverse a curve in the xy plane. Okay, and here's an interesting observation. So the line t, the t line has a preferred direction, right? So the number increases to the right. Right, so t increases to the right. And as t increases from a to b, it'll traverse the curve in a certain direction. So in the way I drew it, it's going to traverse the curve from left to right. But it could be, so I could have a parameterization where a would be mapped to this point and b would be mapped to this point, and then I would do something like this. So it would traverse the curve with the opposite orientation. So that's that notion. So this notion of orientation is going to be important to us. So let me be precise about it. before I move on to computational examples. So orientation of a curve is a very simple thing. So let me draw two copies, twin copies of a curve. So here's the curve. Let me just copy it again. Give you two copies of it. Okay. So an orientation of the curve consists of a direction that I attach to it. So there are two options: this one or this one, right? So it's a physical thing. You can imagine that either particle starts here and ends there, or it starts there and ends here. But I don't care how fast the particle is moving, whether it's like moving really fast at the beginning and then moves slowly, or it's like going at constant speed throughout. That I don't care. I just care whether it's going from A to B or from B to A. So, and I'll have notation. So if I call the curve with one of the orientation C, I'll call the same curve but with the opposite orientation minus C. Right, so if you see a minus sign in front of a curve, that minus is just telling you that I'm looking at the opposite orientation to the original one. If I put a minus sign in front of the curve, it means to begin with I was considering that curve with an orientation, and now I'm looking at the other orientation. Okay, so let's do some examples of parameterizations. So and this is tricky. Like I give you a curve, and your job is to find a parameterization. You have to do it in order to be able to set up an integral afterwards. So let's say we have an ellipse. So I want to show you now a bunch of examples, and in the future, if you find a curve you don't know how to parameterize, you can maybe look at these examples that I'm going to build with you right now, and see if you can get some inspiration here. I think it's useful to have a nice repertoire of examples to draw from. So the first one, so I'll call this example 1, it's going to be an ellipse. So the ellipse has equation 1/4 of x minus 5 squared plus y minus 3 squared equals 1. Okay, so let's draw this. So here's the y-axis, here's the x-axis. So you see this is just so this is an ellipse, and here's what's happening to this shape. I am shifting x to the right by some amount because there's a negative number over here, and I'm shifting. So if I didn't have the 5 and the 3, I would have an ellipse about the origin. If I didn't have the 1/4, I would have a circle around the origin. Now the effect of the 5 and the 3 is to take the shape I would have about the origin and move it to another point. So in this case, I'm going to move it. So the center, instead of being the origin, in our case, is going to be the point 5, 3. So this thing is going to enclose the point 5, 3. So let me draw that point. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4. And then this is, I want the point 5, 3. So that's going to be 1, 2, 3, 4, 5. Okay, so this point right here is not really in our shape, but it's like the origin. It's a reference point. It's where if I didn't have the 5 and the 3, this point would be, the origin would be there. Let me draw now a few points in this ellipse. So let's say, for example, let's look at the points where y is equal to 3. Right, so y minus 3, 0. What points do I get? Well, the equation becomes x minus 5 squared equals 4. So x minus 5 is plus or minus 2. So x minus 5 is plus or minus 2. So x is either 3 or 7. Okay, so if y is 3, then x is 3 or 7. So if y is 3, I get these 2 points, 3 or 7. And now if x is 5, if, on the other hand, x is 5, then the first term vanishes, and then I get that y minus 3 squared is 1, so y minus 3 is plus or minus 1, so y is either 2 or 4. Okay, so y is either 2 or 4. So x is 5, then y is 2 or 4. And so, oh, I drew the wrong point down here. So 2 would be here. This 4 is a little bit too tall. Okay, so the ellipse we're talking about is this one. Right, so now we understand, so we drew a few points. We knew it was a translation of the, so we know an ellipse is something you get by stretching a circle and maybe moving it around. Now we know exactly what we did, so we stretched in the x direction. So we started with a unit circle. It's still in the y direction, the width, the height is still the same. It's still 2 units tall, but now it's 4 units wide rather than 2 units wide. So we stretched it in the x direction by a factor of 2, and then we moved the whole thing away from the origin to encircle the point 5, 3. So this geometric understanding allows us to adapt adapt our construction. So we know how to parameterize a circle, and with this geometric understanding of this ellipse, we can adapt the parameterization of the circle to give me a parameterization of this ellipse. So let's see that happening. So so here's what I'm going to do. So I'm going to shift all points. So 5 is going to be our base point for x, and 3 is going to be our base point for y. Then to 5, I'm going to add not cosine t. So what I'm going to do is guess and check, right? I'm going to start with the parameterization of the circle. So I would have, cosine and sine. I'm going to guess it's going to still have something to do with cosine and sine, but I'm going to modify it a little bit to make sure that the two functions I get over here for x and y, they still satisfy this equation. So let's see. So the key here is I want to stretch in the x direction by 2, and in the y direction I don't want to stretch at all. So I'm just going to multiply the cosine by 2 over here. Just leave the sine as it was. Now, this is my guess for a parameterization of the ellipse. Let's see if the equation is satisfied. So if x is 5 plus 2 cosine t, here x minus 5 is going to be 2 cosine t, so that squared gives me 4 cosine squared t. The 4 then cancels with the denominator, and the first term just gives me cosine squared of t. All right, now let's see what happens when I plug in 3 plus sine in here. Let's check that the equation remains true. So if I plug 3 plus sine in the left hand in place of y, so y minus 3 is just sine squared, right? So this term is sine squared. The first one was cosine squared, and so this equation is telling me, so if I got the parameterization of the ellipse, when I plugged the parameterization into the equation, I was supposed to get, the equation is supposed to remain true for all values of t. And in this case it does, because cosine squared plus sine squared of any angle is equal to 1. Okay, so we guessed and we checked on the equation and it's working. And we want to cover the whole, so here we're just shifting, moving the circle and stretching it. And so we started with the original parameterization of the circle that had t between 0 and 2 pi. I'm going to keep the same because I want to stretch and move the whole circle. I don't want to just stretch and move the upper half of it, for example. So I won't restrict the range of t, I'll just keep it between 0 and 2 pi. And if you want to be sure about the range, for the parameter, you can just check that, when t is 0, I'm over here, just plug in there. When t is 0, I'm over here. When t is pi over 2, I'm up here. When t is pi, I'm up here. And when t is 3 pi over 2, I'm down there. All right. So this is part of the parameterization game. You have to know how to adapt the parameterization. So if you have similar shapes and you know how to parameterize one, you should know you should always try to adapt that parameterization to describe this other similar shape that is given to you. Okay, so that's example number 1. Example number 2 is incredibly easy. So it's a curve that really parameterizes itself. In fact, it's a nice class of curves, so graphs of functions. right? So here's a graph, and it's going to be a curve. Looks like this. I'm going to look at the portion of the graph where x is between a and b, and the graph, of course, has equation y equals f of x. Okay, so how do we parameterize a graph? So again, what does it mean to parameterize? We want to describe points in this graph in terms of a single parameter, single number, right? If I know that number, I know the point. The difficulty usually comes from the fact that, well, the point has two coordinates. Somehow I'm supposed to build two coordinates from one. But the fact that I'm dealing with the graph and I know the function just tells me how to build a point. If I know x, I know that y must be f of x. And so I get the corresponding point. So the parameterization for a graph is I can use as my parameter the x variable itself, and then the point corresponding to a given x value is going to be the point x comma f of x. Right. This is a point in the graph in our curve, and all points in the graph have this shape, and we want the parameter in this case to range between a and b. Right, so here I went back to the R notation. So the first component of R is the x is x in terms of the parameter. If the parameter is x itself, the first component is just x. And the second one is y in terms of the parameter. Here the parameter is x, so y is f of x. Okay, let's look at another, more difficult example. This will be the last example for now, but later when I compute integrals with you guys, you'll see how I go about parameterizing some other curves. But this last example is going to have a few interesting things about it. So the last example is a special curve, a singular curve. So it looks like this. So I can tell you the equation right away. So the equation is y squared equals x cubed. Let me not draw the x-axis. Here, so the curve looks like this. Okay, so I want the portion of this curve. So y squared equals x cubed. It's going to be a curve that looks like this. So I want the portion of this curve that lies between these 2 points, between -1. Sorry, this is positive. Here x is positive and y is negative, and here x is negative and x is positive, and so is y. Okay, so let's see if this picture makes sense. So this picture is suggesting that for every x value, there are gonna be 2 corresponding y values, right? This makes sense because if I fix an x value, then there are 2 solutions. If I fix x, if I fix an x value, there are 2 y values. So the positive and a negative one that satisfy this equation, right? So for each value of x, there are 2 y values. But if x is negative, then x cubed is negative as well, and so there is no solution for y. So y squared would always be positive. If x is negative, this equation doesn't have a solution with that value of x. So this curve is entirely contained in the right half plane, the half plane where x is positive or non-negative, and it looks like this. For each x value, you get 2 y values. And the curvature and it turns out it's convex rather than concave. And the breaking point where the curve has, these 2 points come together is exactly when x is 0, right? Because then the positive and negative square roots of 0 are the same. Non-negative square roots of 0 are the same. All right. So this is our job. Our job is to parameterize this curve. I will call it C. Okay, so how are we gonna go about this? So there are 2 ways. One is there's the tricky way, and there is the more dependable way. So let me show you the dependable way first. This curve, it has two parts to it. It has this upper part and this lower part. Oh, now that I'm drawing the curve, I just realized I want to parameterize this curve, but I'm giving the curve a particular orientation. So I want the curve that starts at this point and then moves here and then goes to the other side. Right? I want this shape plus this given orientation. So you'll see what I'm going to do at the end, how this is going to affect my answer. So if we have a curve that naturally breaks into two pieces, a perfectly nice answer for how do you parameterize it is to say, okay, here's how you parameterize each piece. That's my answer. You don't need. It's seldom useful to put the two parameterizations together. So it's fine if you. So when I ask for a parameterization of a curve, it's fine if you give me several parameterizations for several pieces that make up the curve. So that's what I'm going to do here. In the first, dependable method, I'll just parameterize this half and then parameterize the lower half. Okay, so I'm going to say that my curve is C is C1, the upper half, plus, or union, let me just say union for now, C2. And C2, so C1 is this upper half, and C2 is the lower half. Okay, so now let's see if we can parameterize C1. So C1, so do you see, so C1 is this upper half. On C1, y is always non-negative. So this equation is telling me that y is the non-negative square root of x cubed. Right? On C1, y is a non-negative square root of c cubed. So in other words, I can say, so here's my solution. On C1, I'm just going to solve this equation for y. So I'm going to say, I'm going to have two parameters. So you see that on C1, I can express y in terms of x. I can solve this equation for y without any ambiguity, any sign ambiguity. I can just say that y is the positive square root of x cubed, that's x to the 3 halves. All right, so I have this, and then I look at this and say, okay, I already know I have y in terms of x, so I can just say that x is itself, and there I have my parameterization. I just say that the parameter, so x ranges between 0, so on C1, x ranges between 0 and 1. Okay, now on C2, I can basically do the same thing. To parameterize this lower half, I can basically do the same thing. Just note on C2, I know for a fact that y is always negative, and so there's no ambiguity. I know that y is the negative square root of x cubed. So y is minus the positive square root of x cubed. So y is minus x to the 3 halves. And x is, of course, itself. And then to cover the whole of C2, I need all x's between 0 and 1. So I'm looking at x's between 0 and 1. Okay. Now, here's a problem. We are almost done, except that I said, so at the beginning of the problem I said for this curve, whatever we're going to do with it next, for that we're going to need the curve parameterized as I drew it, right? So starting at 1, -1, then going to 0, then going up. But so C1 is fine because when x increases from 0 to 1, I'm moving like this. So I'm following along the given parameterization for C. But C2 is not fine. When x is 0 on C2, I get the point 0, 0. When x is 1, I get the point 1, comma, -1. So I'm down there. So C2 is going in the opposite orientation. So sorry, this parameterization is not giving me C2. It's actually giving me minus C2. And so so this is something you could fix. I could change my parameter. So this is something you can fix, but you probably don't want to. So for many purposes, if you know a parameterization of minus the curve, you can do the calculation with that, with the parameterization minus the curve. So for the opposite orientation, and then just flip a sign at the end for your answer. But if you really want to have a parameterization of C2, here's what you do. You replace, so let's see, when x increases from 0 to 1, so let t be 1 minus x. Just look at what happens to 1 minus x. When x is 0, t starts at 1, and then when x is 1, so as x increases, t decreases and then stops at 0. So it goes backwards. So that's what I'm going to do here. I'm going to flip this x here to 1 minus t. So x is 1 minus t. And then t is going to increase from 0 to 1. Okay, so this way, so instead of having x be itself, x is going to be 1 minus t. So it's basically x, but it starts, instead of starting at the origin, it starts at 1 and then moves to the left as t increases. And move leftwards. So this is going to cover the x-axis, but leftwards, and it fixes the problem we had. Now C2 is going to do have the correct trajectory, the correct orientation. So that's the dependable way of getting a parameterization. If I give you an equation for the curve, you just solve the equation, and if there's some sign ambiguity or some other reason to break the curve, you break the curve until you're able to definitively write one variable in terms of the other, and then you just use this other variable as your parameter. And if there are orientation issues, this trick is always going to work. Okay, so the other solution to this case, in this case, is going to, excuse me. So the other solution to the problem of parameterizing this curve actually gives you a much better parameterization. It's easier to compute integrals with this other better parameterization. So it's better only because it's easier to compute with. And here it is. So I want some parameter between two numbers, and x and y in terms of this parameter. So I want formulas for x and y in terms of a parameter t that always satisfy this equation. But I don't want, so my original formulas had square roots, right? They're hidden over here. 3/2 is a square root of 3 cubed. I don't want square roots. I just want easy formulas for x and y, polynomial formulas for x and y that satisfy this equation. It turns out we can't find these formulas. So if I say that x is t squared and y is t cubed, right? If I do this, then the left side of the equation becomes 3 cubed squared, that's t to the 6. The right-hand side becomes t squared cubed, that's t to the 6, right? X cubed is t to the 6 as well. So I always get, so if for any value of t, I always get points on this curve, but I don't want the whole curve, I just want the segment of the portion of the curve that, I'm cutting the curve off at these 2 points. So I want to bound t so as to respect this cutoff. I think here I want to have t go from -1 to 1. Right, this way, when t is -1, I get -1 squared, that's 1, and -1. So I start over here. Then t increases, as it goes toward 1, it passes through 0. When t is 0, x and y are both 0, I'm here. And then when t is 1, I'm at the correct end. So this gives me exactly the whole segment in a single swoop. So this is just to show you that sometimes, so there are easier and harder parameterizations. So this would be easier to work with if you were computing an integral, and this would be slightly harder. All right, so this was hard work, setting up, doing all this preparation, but it's going to pay off. Now, talking about the line integrals is going to be easier. So let's do that. So line integrals. So I'm going to approach line integrals from, so I'm going to motivate line integrals from the problem of computing the length of a curve, right? So I should warn you that we're going to learn how to do two kinds of line integrals. We'll know. So if I give you a curve, let me just draw a curve so we can start looking at it. So here's the xy plane, and here is a nice curve. Okay, so there's our curve. I'll call it C even. So later we'll know how to do things like integral over C of f of x, y, ds. Or we'll learn how to do integral over C of a vector field times dr. Right? So we'll learn how to do two kinds of integrals. We'll know how to integrate functions over curves and vector fields over curves. So first we'll learn how to do functions. It turns out that this other one, the integral of a vector field, is a special case of the other one. So, but before we do all that, let's talk about the length of C. It's going to lead us in the right direction. So here's how. So the length of C is defined like this. So it's defined by a kind of a Riemann sum. It's a special case of a Riemann sum. So the length. Just a moment, please. So the length of C is, I can compute it like this. I'm going to break my curve into a bunch of points, using a bunch of points, maybe 1,000,000 points, right? There will be point number 1, point number 2, all the way to point number 1,000,000. So let me call these 2 points, so I'm going to get a bunch of these. I drew 2 of them. So a given point, the ith point and the next. Maybe I don't want to. Oh. Just a sec. Okay, so I have these 2 points. I'm going to have a bunch of these. And then when I'm looking at the ith point, I'm going to ask, what's the distance between this point and the next? So this distance will be delta Si. So delta Si is the distance from the ith point to the next, and I'm going to have a bunch of these throughout my curve. And I'm going to add all of these. So I'm going to add all of these delta Si's. So these are really distances. So lengths of. So delta Si is the length of this line segment joining xi and xi plus 1. I mean the ith point and the I plus first point. I'm going to add the distances of these little line segments. And then I'm going to take a limit, so I get a sum. And given a subdivision of the curve, I'm going to get a sum. And this sum is going to become a better and better approximation of the length of the curve when the subdivisions become smaller and smaller. So I'm just going to say that the limit as delta Si goes to 0, so this is the Riemann sums sense of these sums, of these, these little distances between consecutive points, that gives us in the limit the length of the curve, of this curvilinear shape. All right. Now, it turns out that if I have so this is the theoretical definition of the length. Maybe so. This is how we define it. Of course, given this is just a sketch, I would need to make this mathematically rigorous. I would have to explain this limit better. But I think the main ideas of the definition are here. Now, let me show you how we can compute this. So if we have a parameterization of the curve, let me just write down a parameterization. So let's say I have a parameterization. R of t is So I have a x of t comma y of t. Right? This r is a parameterization of the curve, and I'm saying that t is between a and b, between two numbers. Right, so here's the t line, and here's a, here's the point in the middle, t, and here's b. ti. Oh, well, t, okay. Let's think about t in a moment. Right, and the parameterization gives me points in the curve. So A corresponds to this point over here, R of A, and B, just the parameterization, if I plug B in, I get the other endpoint, R of B. Okay, so if I have the parameterization, in other words, if I have X and Y on this curve in terms of a single parameter T, I can express the length of the curve I can compute the length of the curve as an integral. So here's that integral. So the length is just equal to the integral for t going between a and b of the square root of dx dt squared plus dy dt squared. So this is a function of t, and then you multiply that by dt and integrate. So there you go. Turns out that you can compute the length of a curve just by integrating this funny looking square root. Okay, so but you don't have to believe me. Let me tell you why. So here's why this formula works. So here's why. So let's look at these things we're adding. So delta SI. So delta SI is by Pythagoras' theorem. So you can put delta SI in a triangle, right? So let me just look at the difference, the x coordinates of the 2 points. So this distance, let me call it delta xi, and let me call the difference in the heights of the 2 points delta yi. Right? Then delta SI by Pythagoras' theorem is just equal to delta xi squared, the square root of this sum here. Okay, so the formula I gave you is starting to look less suspicious, right? There is a square root, there are squares, there is x and y. Okay, let me try to make this formula, this integral formula for the length, even less mysterious. So I'm going to divide everything inside the square root. So what I'm going to do next works for any positive real number. So let's suppose that I have a positive real number with a funny name. It's called delta ti. So I'm going to divide everything inside the square root by delta ti squared. I'm going to get delta xi divided by delta ti, and then delta yi divided by delta ti. And then I'll multiply the whole thing by delta ti. So this was equal to that by Pythagoras, and these are equal to each other by algebra, because the square in the denominator disappears with the root, and then the denominator cancels the thing I multiplied. So if I give you any non-negative number, any positive number delta ti, and just divide this equation, divide and multiply this equation by that number, and I'm going to get this, which is basically the thing I'm integrating, I'm adding when I do this Riemann sum. So I think this gives even more credibility to my claim that the length is an integral of this kind. Now, to really kill this issue, to bring it down, let me explain exactly what's going on, why this length is equal to this integral. So here's why. So the length is equal to a sum like this, is approximated by a sum like this, provided that these separations are really small. So I need to produce, to get close to the length, I need to produce a subdivision of my curve where the separations are really, really small. Here's how I'm going to do this. Produce a separation that's going to help me compute the length. I'm going, instead of trying to produce a separation on a bunch of partition of the curve directly, I'm going to partition the interval AB, and then I'm going to use my parameterization, and then, right, so there's going to be TI plus 1, right, and then each of these is going to give me a point on the curve. Right, I'm going to have a partition of this interval, and then right, and then so once I have a partition of this interval AB, that's going to give me a partition by using the parameterization partition of the curve. So now when we look at this integral over here, we're really partitioning this curve and then multiplying, evaluating the square root and multiplying by delta t, by the interval between two points in the partition. So I'm multiplying by this interval over here, delta ti, right? The distance between ti and the next and ti plus 1. So I'm multiplying, taking this square root and multiplying, evaluating at the ith point, and then multiplying by delta ti. Now, observe that this square root is basically this square root, right? The derivative is, you just increase, you see how much, you increase t and see how much x changes when you do that, right? So you move from here to here and see how much x changes, from here to here. Move to the right a little bit. And then, so this quotient is basically, approximates this derivative. So the quotient squared approximates the other derivative, and similarly here. So I hope this hand waving convinced you that the length is given by that, by this integral. So it's going to be useful in the future to put this sort of expression together. So this is going to be ds, the arc length element on the curve. So the infinitesimal arc length element on the curve. And the point is that this expression, when I replace the d's, which are infinitesimal, by deltas, which are finite differences, then I'm going to get an approximation for the distance. I'm going to get the distance between two close by points on my curve. And when I add these arc lengths element, these little pieces of length in the curve, when I add over the whole curve, I get the length of the curve. All right. So, okay. So I think I'm going to. I don't want to, stretch your patience. So I will under-deliver on the promise. I will give you the definition of a line integral at the beginning of the next lecture, when everybody's going to be feeling, fresh and energized. But I laid out the groundwork for that, and so I hope that discussion will run smoothly. It's a very, very important moment in this class, so that's why I planned everything out so the discussion would be smooth, would have as few bumps as possible. Anyway, so this is a good place to stop. Thanks for listening, and I'll see you guys when I record the next video. Bye-bye.